On July 20th, 1969, at 20 hours 17 minutes and 40 seconds Coordinated Universal Time, a human voice crackled across 384,000 kilometers of empty space and said 8 words that stopped the world. Houston, Tranquility Base here. The Eagle has landed. In mission control in Houston, Texas, men who had spent years of their lives working toward this moment broke down and wept at their consoles. In living rooms across the United States and around the world, hundreds of millions of people sat in front of their television sets and felt something that most of them had never felt before and would never feel in quite the same way again. A species that had spent all of its existence on one small planet had just set foot on another world. Tonight, we go to that world, the moon, and to the specific place on the moon where it happened, a vast, ancient plain of dark volcanic rock named by astronomers 4 centuries ago, with a name that feels almost impossibly appropriate for a sleep story, the Sea of Tranquility. Everything I am going to tell you is true. Every measurement, every detail, every moment. This is the real moon, the real mission, the real history. And by the time we are finished, you will understand this world that hangs in the sky above you every night in a way that most people never stop to consider. Before we go any further, take a slow breath in, let your lungs fill gently, hold it for a moment, and breathe out slowly, feeling your whole body settle and release. Feel where you are lying, feel the warmth around you. Let your eyes stay closed and heavy. You are safe and comfortable, and we are about to revisit one of the most extraordinary moments in human history and the extraordinary world where it took place. Let us begin at the very beginning, not in 1969, but 4.5 billion years earlier. Let us begin with the origin of the moon itself. The moon was not always there. In the earliest period of the solar system, Earth had no large moon. The solar system was a chaotic place, full of rocky bodies of all sizes orbiting the young sun, colliding and merging and growing. About 4.5 billion years ago, somewhere between 30 million and 100 million years after the formation of the solar system, something happened that changed Earth permanently. A protoplanet, roughly the size of Mars, collided with the young Earth. Scientists call this protoplanet Theia. The collision was not a glancing blow. It was an enormous impact, a collision of such violence that it would be almost impossible to describe in terms that convey its true scale. The impacting body struck Earth at tens of thousands of kilometers per hour. The energy released was incomprehensible. Both bodies were largely vaporized and melted by the impact. Enormous amounts of material were flung outward from the collision in all directions, forming a ring of debris that surrounded the early Earth. Over a period of perhaps a few thousand years, this ring of debris coalesced under gravity. The smaller pieces clumped together. The clumps attracted more material, larger aggregations formed, and eventually, within a geological instant, the moon formed from this ring of debris, orbiting much closer to Earth than it does today. This is called the giant impact hypothesis, and it is supported by several lines of evidence. The composition of the moon's rocks, as measured by Apollo samples and lunar meteorites found on Earth, is remarkably similar to Earth's mantle rocks. The moon has almost no iron, consistent with the formation from the outer layers of Earth and Theia after the iron cores of both bodies had already separated downward. The moon has almost no volatile elements, substances that evaporate at relatively low temperatures, consistent with the extreme heating that would have occurred in such a violent impact. And the moon's orbit and the Earth's rotation are consistent with the angular momentum that would have been introduced by a large oblique impact. The young moon, in the immediate aftermath of its formation, was very different from the moon we see today. It was much closer to Earth. Its surface was molten, covered by a magma ocean kilometers deep. The tides it raised on Earth were enormous. The Earth itself rotated much faster, with a day lasting only 5 or 6 hours. The moon's gravity was slowing Earth's rotation through tidal friction, transferring angular momentum from Earth's spin to the moon's orbit. As Earth slowed, the moon moved outward, and it has been moving outward ever since, at a rate of about 3.8 centimeters per year. Over the first billion years of the moon's existence, its surface was subjected to an intense period of meteorite bombardment. The tail end of the violent early solar system, when enormous quantities of rocky debris were still flying through the inner solar system. This bombardment, called the Late Heavy Bombardment, created the moon's highlands, the light-colored, heavily cratered terrain that covers much of the lunar surface. The highlands are the ancient, battered crust of the moon, reworked by billions of years of impacts into the pale, cratered landscape visible through even a small telescope. But between about 4 billion and 2.5 billion years ago, a different process was at work. The interior of the moon, still hot from its violent formation and from the decay of radioactive elements, produced enormous volumes of basaltic lava. This lava erupted from fissures in the moon's crust and flooded into the largest impact basins, the deep depressions created by the most enormous impacts of the early solar system. The lava flowed and spread and cooled and hardened into dark, smooth plains. The contrast between the pale highlands and the dark lava plains is visible to the naked eye from Earth. The pale regions are the ancient cratered highlands, the dark regions are the volcanic plains, and the volcanic plains are what ancient astronomers, looking at the moon with naked eyes centuries ago, imagined to be actual seas. They called them Maria, the Latin word for seas. Individual seas were given names reflecting the moods and phenomena of water: the Sea of Tranquility, the Sea of Serenity, the Sea of Crisis, the Ocean of Storms, the Sea of Moisture, the Lake of Dreams. None of them have ever contained water. They have never been liquid in any way that would float a ship. They are dark, ancient volcanic rock, solidified billions of years ago and sitting unchanged, or nearly unchanged, ever since. But the name stuck, and it is in the Sea of Tranquility, the Mare Tranquillitatis, that humanity first set foot on another world. The Sea of Tranquility is located in the northeastern quadrant of the moon's near side, the side that always faces Earth. It covers an area of about 873,000 square kilometers, roughly the size of Egypt. It is an ancient lava plain formed between about 3.6 and 3. 9 billion years ago, when lava flooded the basin and cooled into the dark basaltic rock that now forms its surface. The rock is a form of basalt, similar to the basalt that forms the ocean floors on Earth and the volcanic islands of Hawaii. It is dark because it is rich in iron and magnesium minerals that absorb sunlight efficiently. The surface of the Sea of Tranquility is not perfectly flat. There are craters scattered across it, formed by meteorite impacts over the billions of years since the lava cooled. Some of these craters are ancient and heavily eroded by billions of years of micrometeorite bombardment. Others are younger and fresher, with sharp rims and bright ejecta rays radiating outward from the impact point. There are gentle hills and low ridges formed by the cooling and contraction of the ancient lava. There are sinuous rills, long, narrow valleys that may mark the paths of ancient lava tubes that collapsed after the lava inside them drained away. The Sea of Tranquility is, despite its name, a landscape with character and history, not a featureless flat plain. The surface of the moon everywhere, including the Sea of Tranquility, is covered by a layer of fine, powdery material called regolith. This is not soil in the biological sense. There are no organic compounds in it, no moisture, no biological processes that have ever acted on it. It is a mechanical mixture of fine rock particles produced by billions of years of meteorite impacts grinding and pulverizing the surface rock. The regolith of the Lunar Maria is typically a few meters deep, overlying the solid basalt below. It is grayish in color, though it can appear brownish or tan in certain lighting conditions. It is extremely fine, with grain sizes ranging from large rock fragments down to particles too small to see without a microscope. The footprints left in the lunar regolith on July 20th, 1969 are almost certainly still there today. The moon has no atmosphere to carry wind that could fill them in. It has no liquid water to erode them. Micrometeorite bombardment will gradually degrade them over millions of years, but slowly enough that they will remain recognizable for far longer than human civilization has existed. The footprints of Neil Armstrong and Buzz Aldrin in the Sea of Tranquility may outlast every building ever built on Earth. Your breathing is slowing beautifully. Let it settle even more. We are moving toward the story of the mission itself, toward the moment those footprints were made, and toward everything that had to happen to make that moment possible. Let us set the scene. The year is 1969. The world is very different from the world you inhabit. The Cold War between the United States and the Soviet Union has shaped global politics for more than 2 decades. The two superpowers are locked in competition across every domain: military, economic, ideological, and technological. Space is one of the most visible arenas of this competition. The Soviet Union launched the first satellite, Sputnik, in 1957. It sent the first human into space, Yuri Gagarin, in 1961. In almost every milestone of the early space age, the Soviets have been first. Then, on May 25, 1961, President John F. Kennedy stood before a joint session of Congress and made one of the most audacious commitments in the history of politics. He proposed that the United States should commit itself to achieving the goal before the decade is out of landing a man on the moon and returning him safely to Earth. It was a commitment made when the United States had less than 15 minutes of human spaceflight experience. It was a commitment to accomplish something that no one in the world yet knew how to do. It was a commitment to solve thousands of technical problems that had never been solved before, to invent technologies that did not yet exist, and to do all of it in less than 9 years. The Apollo program was the response to that commitment. At its peak, The Apollo program employed more than 400,000 people. It consumed roughly 4% of the U.S. federal budget. It drove the development of new materials, new manufacturing techniques, new computational methods, new management approaches, and new engineering disciplines. It was the largest peacetime mobilization of human talent and resources in history. 7 years after Kennedy's speech, most of those problems had been solved. The Saturn V rocket, the most powerful launch vehicle ever built, had been successfully tested. The Apollo spacecraft, consisting of the command module and the lunar module, had been designed and built and tested. 6 manned Apollo missions had flown. Apollo 1 had ended in tragedy, a launch pad fire killing 3 astronauts. Apollo 8 had carried humans to lunar orbit and back for the first time. Apollo 9 had tested the lunar module in Earth orbit. Apollo 10 had flown the lunar module to within 15 kilometers of the lunar surface, a dress rehearsal for the landing. Everything was ready. Apollo 11 was launched on July 16, 1969 at 9:32 in the morning Eastern Time from Launch Complex 39A at the Kennedy Space Center in Florida. The Saturn V rocket that propelled it stands 111 meters tall, about the height of a 36-story building. It weighed, fully fueled, about 2.8 million kilograms. It produced 34 million newtons of thrust at liftoff. The noise it made during launch was so intense that it could be felt as a physical sensation in the body of anyone standing within kilometers of the launch pad. An estimated 1 million people had gathered in the surrounding area to watch the launch. Many more hundreds of millions watched on television. The crew consisted of 3 men. Neil Armstrong, the mission commander, was 38 years old. He was a quiet, thoughtful man, a former naval aviator and test pilot who had flown the X-15 rocket plane to the edge of space. He had already flown in space on Gemini 8, during which he had performed the first successful docking of 2 spacecraft in orbit, and had used manual control to prevent a stuck thruster from sending the spacecraft into an uncontrolled spin. He was chosen to be the first person to walk on the moon, in part because of his calm, his skill, and his character. He was not a man who would be overwhelmed by the moment. Edwin Aldrin, who preferred to be called Buzz, was the lunar module pilot. He was 39 years old, also a former military pilot and a veteran of the Gemini program. He held a doctorate in astronautics from MIT. He had previously set a spacewalk record of 5.5 hours on Gemini 12. He would become the second person to walk on the moon, following Armstrong down the ladder of the Eagle. Michael Collins was the command module pilot. He was 38 years old and had also flown on Gemini 10. His role in the mission was to remain in orbit around the moon in the command module, called Columbia, while Armstrong and Aldrin descended to the surface. He would orbit the moon alone, not quite out of radio contact with Earth, but unable to communicate with Armstrong and Aldrin when the orbit carried him around the far side of the moon. He spent about 48 minutes of every 2-hour orbit out of contact with all of humanity, more alone than any human being had ever been. He has described this not as lonely, but as peaceful. The journey from Earth to the moon took 3 days. The astronauts traveled in the command module attached to the service module that carried the propulsion systems and supplies. The lunar module rode below them in a protective housing at the top of the 3rd stage of the Saturn V rocket. On the way to the moon, they performed a transposition and docking maneuver, separating the command module from the rocket stage, turning it around, and docking with the lunar module to extract it for the journey ahead. On July 19, Apollo 11 entered lunar orbit. The engine burn that slowed the spacecraft enough to be captured by the moon's gravity lasted about 6 minutes. When it was complete, the astronauts were in an elliptical orbit around the moon, passing about 100 kilometers above the surface at its closest point. They spent about 24 hours in lunar orbit studying the landing site, checking the spacecraft systems, and preparing for the landing. On July 20, Armstrong and Aldrin transferred into the lunar module called Eagle. Collins sealed the hatch between the two spacecraft. The Eagle undocked from Columbia and began the powered descent toward the surface. Collins would orbit alone, watching the landing site through binoculars when his orbit brought him over it, until the Eagle returned. The descent to the surface was one of the most tense and dramatic sequences in the history of spaceflight. As the lunar module fired its descent engine and began moving toward the surface, the onboard computer suddenly displayed an alarm code that no one had seen outside of a simulation. Program Alarm 1202. The mission controllers in Houston, some of them barely into their 20s, had to make a rapid decision. Was this alarm serious enough to abort the landing? The answer came quickly. Steve Bales, a 26-year-old guidance officer who had studied all the possible alarms exhaustively, recognized the 1202 alarm as an executive overflow, meaning the computer was taking on more tasks than it could handle at once, and was dumping lower priority tasks to deal with the critical ones. It was serious, but not mission-ending. Bales told his supervisor to continue. The landing continued. At about 600 meters altitude, Armstrong looked out the window and saw that the computer was guiding the Eagle toward a large, boulder-strewn crater, not a suitable landing site. He took manual control of the lunar module and flew it forward over the crater, looking for a safer place to set down. Every second of flying used precious fuel. The landing radar showed 60 meters of altitude. Then, 30. Fuel was becoming critical. A few more seconds and they would be required to abort and return to orbit. Then, 9 meters. The surface dust was blowing in all directions from the descent engine. Then the contact probes extending below the landing legs touched the surface. A light on the instrument panel came on, and Armstrong cut the engine. The lunar module settled. There was silence for a moment. Then Armstrong's voice, calm and measured even in this historic moment, came across the radio link to mission control. Houston, Tranquility Base. The Eagle has landed. In mission control, there was an explosion of cheers and applause and tears. The tension of the past hours released all at once. They had done it. They had actually done it. After the space of a breath, the flight director, Charlie Duke, keyed his microphone and said, "Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot." The Eagle had landed in the southwestern part of the Sea of Tranquility, about 6 kilometers west of the planned landing site. The deviation was caused by Armstrong's decision to fly past the boulder-strewn crater. The actual landing coordinates are 0 degrees 40 minutes 26.69 seconds north latitude and 23 degrees 28 minutes 22.69 seconds east longitude. These precise numbers mark a point on the moon's surface where two human beings stood for the first time in the history of the solar system. Let your breathing settle deeper now. Let the weight of that moment rest gently in your thoughts. Two human beings, descended from people who never left the plains of Africa, standing on another world. The silence of the moon around them, the earth hanging in the black sky above. Let it be still. Let it be peaceful. Armstrong and Aldrin spent about 6.5 hours inside the Eagle after landing, checking spacecraft systems and resting, though neither of them could sleep. At 2:56 UTC on July 21, Armstrong opened the Eagle's hatch. He climbed down the 9 rungs of the ladder to the final rung, paused, and dropped to the surface. He took a few steps, and then he said the words that had been prepared for this moment. That's one small step for man, one giant leap for mankind. Armstrong had intended to say one small step for a man, but the article was lost in transmission or in the speaking. The meaning was clear regardless. Humanity had walked on the moon. Buzz Aldrin joined Armstrong on the surface about 20 minutes later. His first words upon seeing the landscape around him were 3 words that have become famous for their sparse and perfect accuracy: magnificent desolation. The landscape of the Sea of Tranquility stretches away in all directions, gray and powdery and dotted with small craters and rocks, under a sky that is absolutely black despite the blazing sun. There is no blue scattering of the atmosphere. No haze on the horizon. The horizon itself is close, only about 2.5 kilometers away, because the moon is so much smaller than Earth that its surface curves away more rapidly. The astronauts spent 2 hours and 31 minutes outside the Eagle. They photographed everything. They collected samples of rock and soil, filling bags and containers with materials that were brought back to Earth for analysis. They deployed scientific instruments, including a seismometer to detect moonquakes, a laser retroreflector that astronomers on Earth still use today to measure the precise distance to the moon by bouncing laser pulses off it, and a solar wind composition experiment that collected particles from the sun. They planted an American flag, carefully designed with a horizontal rod at the top to keep it extended in the absence of wind. And they had a conversation transmitted live to Earth with President Nixon. The rock samples that Armstrong and Aldrin brought back from the Sea of Tranquility are among the most scientifically valuable objects in human possession. The 21.55 kilograms of lunar material collected during Apollo 11 and the more than 380 kilograms of total lunar material collected during all 6 successful Apollo landings have been studied by thousands of scientists and dozens of countries over more than 50 years. They have told us things about the moon's formation, its geological history, its internal structure, and its relationship to Earth that could not have been learned any other way. The rocks confirmed that the mere basalts of the Sea of Tranquility are indeed volcanic. Similar in many ways to the basalt of Earth's ocean floors, but with specific differences in composition that reflect the particular conditions of the moon's interior and the ancient lava flows that produced them. The rocks are extremely old, with ages between 3.6 and 3.9 billion years, measured by radioactive dating. They have never been disturbed by weather or water or biological processes. They carry an unmodified record of conditions in the early solar system that has been erased from all accessible Earth rocks by 4 billion years of geological activity. Every analysis of a lunar sample is like reading a message written in the earliest chapter of the solar system's history. The ascent from the Sea of Tranquility was itself a remarkable moment. The descent stage of the lunar module remained on the surface, acting as a launch pad. The ascent stage, containing Armstrong and Aldrin, fired its single engine and rose from the surface. If that engine had failed to ignite, there was no backup. There was no rescue mission. Armstrong and Aldrin would have been stranded on the moon. But the engine fired perfectly. The Eagle rose from the Sea of Tranquility, leaving behind the descent stage with its cargo of memories. They rendezvoused with Collins in lunar orbit, docked, and began the journey home. Apollo 11 splashed down in the Pacific Ocean on July 24, 1969. The 3 astronauts were recovered by US Hornet and placed in a quarantine facility for 21 days, as a precaution against the possibility that they had brought back unknown lunar pathogens. They had not, but the caution was reasonable given that no one had ever brought material from another world to Earth before. The legacy of Apollo 11 is complex and profound. It demonstrated that human beings are capable of extraordinary technological achievement when sufficiently motivated. It provided scientific information about the moon that transformed planetary science. It inspired generations of scientists, engineers, and explorers, and it remains, more than 50 years later, one of the clearest examples of what human beings can accomplish when they are determined enough. Of the 12 people who walked on the moon during the Apollo program, all walked on it between 1969 and 1972. The last human footstep on the moon was taken on December 14, 1972, by Gene Cernan, the commander of Apollo 17. He was the last person to climb the ladder back into the lunar module, and so was the last human being to stand on the surface of the moon. He has said that as he climbed the ladder. He paused and looked down at his footprint in the soil and thought about what it meant. No human being has stood on the moon since then. For more than 50 years, the footprints left by Apollo astronauts have sat undisturbed in the regolith of the Sea of Tranquility and 5 other landing sites across the lunar surface. The scientific instruments they deployed continued transmitting data for years. The laser retroreflectors are still in use today, allowing astronomers to measure the moon's distance to an accuracy of a few centimeters and to track the slow drift of the moon away from Earth. The moon's influence on Earth extends far beyond the cultural and scientific legacy of Apollo. The moon plays a fundamental physical role in Earth's existence. Its gravitational pull creates the tides, the twice daily rise and fall of the oceans that has shaped coastlines, driven evolution, and influenced the rhythms of biology for billions of years. The moon's gravity also stabilizes Earth's axial tilt, keeping it at roughly 23.5 degrees rather than allowing it to vary wildly over time. This stability of the axial tilt is crucial for maintaining the stability of Earth's seasons and climate. Without the moon's stabilizing influence, Earth's axis might wobble dramatically over timescales of millions of years, causing extreme climate variations that could make long-term biological evolution much more difficult. The moon is also slowly taking energy away from Earth's rotation. Tidal friction between the oceans and the solid Earth gradually slows Earth's spin. This energy is transferred to the moon, pushing it slightly farther away with each passing year. Billions of years ago, when the moon was much closer, days were much shorter, the tides were much higher, and the moon appeared much larger in the sky. Far from being a passive backdrop to Earth's story, the moon is an active participant in it. It was involved in the formation of Earth's early ocean through the enormous tides that mixed and stirred the early seas. It may have played a role in the origin of life by driving tidal cycles that concentrated organic molecules in coastal pools and subjected them to wet-dry cycles that could have aided the formation of complex biological molecules. It has protected Earth's climate stability for billions of years, and it gave us the nightlight that has guided every navigator and poet and lover who has walked beneath it. NASA's Artemis program, currently in development, aims to return humans to the moon, including the first woman and the first person of color to walk on the lunar surface. The initial Artemis missions are targeted for the lunar South Polar region, where permanently shadowed craters are thought to contain water ice that could be used to support a sustained human presence. The South Polar water ice, if confirmed in accessible quantities and forms, would be one of the most valuable resources in the inner solar system, providing water for drinking, and oxygen for breathing, and hydrogen for rocket propellant. When the first Artemis astronauts descend to the lunar surface, they will be working in a very different environment from the equatorial landing sites of the Apollo era. The South Polar region has a different lighting and thermal environment. The craters near the pole are in permanent shadow, never receiving direct sunlight. The peaks between them catch sunlight nearly continuously. The terrain is more rugged. The scientific questions are different, but the fundamental experience, that of standing on the surface of another world and looking up at Earth hanging in the black sky, will be the same. Let us spend a moment thinking about what Michael Collins experienced during those hours while Armstrong and Aldrin were on the surface below him. Collins orbited the moon alone in Columbia, completing orbit after orbit, watching the surface pass beneath him. He passed over the landing site several times during his solo orbits, trying to spot the eagle with his binoculars, but the lunar module was too small to be resolved from that altitude. Every 2 hours, Collins's orbit carried him around the far side of the moon, out of contact with Earth and out of contact with Armstrong and Aldrin. During these periods, lasting about 48 minutes, he was more isolated from other human beings than anyone in history. If he had a problem, there was no one to help him. If the spacecraft failed, no rescue was coming. He orbited in total radio silence, looking out at the stark black sky and the gray curved surface of the moon below and the stars beyond, completely alone. Collins has spoken about this solitude in interviews over the years, and his description of it is striking. He did not feel lonely, he says. He felt serene. He felt comfortable with the solitude. He was aware of its historical unusualness, aware that no human being had ever been that isolated before. But he did not find it frightening. He found it peaceful. His task was clear, and his spacecraft was functioning, He had faith in the system and in his crewmates. He orbited and waited. On his 14th orbit, as he came around the eastern limb of the moon, he heard Armstrong's voice. Eagle has wings. They had lifted off from the surface. The ascent had worked. Collins had spent the previous hours preparing for the reunion, but also preparing for the worst. If Eagle had failed to launch, Collins had been instructed to return to Earth alone. He has said that this was the least appealing instruction he ever received from NASA. He had resigned himself to the possibility, but found comfort in the knowledge that Armstrong and Aldrin would have faced their situation with the same professional equanimity they brought to everything else. The rendezvous between Eagle and Columbia was a complex ballet of orbital mechanics. The ascending Eagle had to reach the right altitude and velocity at the right point in its orbit to intersect Columbia's path. Collins, watching from Columbia, guided the final approach with practiced skill. The two spacecraft docked. The hatch opened. Armstrong floated through from the lunar module into the command module. Collins looked at him and said, simply, "How is the moon?" Armstrong smiled and said, "It is fine." Then Aldrin followed. The three astronauts were together again for the first time in almost a day. Now let us think about the moon's geology in more depth. Because the Sea of Tranquility and the other landing sites of the Apollo program have revealed an extraordinary record of the early solar system. The basalt of the Sea of Tranquility is between 3.6 and 3.9 billion years old. This means it cooled and solidified when life on Earth was only in its most primitive microbial form, when the continents were beginning to form and oceans covered most of the planet, when the atmosphere was very different from what it is today. The rocks that Armstrong and Aldrin picked up from the surface of the moon are older than any intact rock formation accessible on Earth. Earth's geological activity, the constant recycling of the crust through plate tectonics, has destroyed almost all of Earth's oldest rocks, but the moon has no plate tectonics. Its geological activity stopped billions of years ago. The rocks from the Sea of Tranquility have been sitting in essentially the same state since they cooled from lava, undisturbed by any geological process, exposed only to space weathering and occasional impact gardening. Space weathering is the process by which the surfaces of airless bodies are altered by exposure to the space environment. On the moon, space weathering is driven primarily by the solar wind, a continuous stream of charged particles flowing outward from the sun, and by micrometeorite bombardment, the continuous rain of tiny particles that strike the surface at high velocity. Over millions of years, these processes alter the chemistry and optical properties of the surface minerals, darkening them and creating thin coatings of glassy material on the surfaces of individual mineral grains. Space weathering is one of the reasons the lunar surface appears gray, rather than the original colors of the minerals it contains. The regolith, the fine surface layer of powdered rock, is itself a product of billions of years of meteorite impacts at every scale. Every impact, from the enormous ancient impacts that formed the Mare Basins to the tiny micrometeorites striking the surface continuously right now at this moment, contributes to the grinding of rock into smaller and smaller fragments. The regolith of the Sea of Tranquility is a mixture of rock fragments of all sizes, from centimeters down to micrometers, mixed with glass spheres formed when impacts melted rock and flung the molten droplets into the air before they cooled in flight. There are also agglutinates, complex particles formed when micrometeorite impacts weld small soil grains together into irregular clumps with their surfaces coated in glass. The regolith is a rich record of the processes that have acted on the lunar surface, preserved in the specific distribution and character of its particles. The Apollo seismometers revealed something surprising about the moon's interior. When seismic waves from moonquakes or from the deliberate impacts of spent rocket stages traveled through the moon, they behaved differently from how seismic waves travel through Earth's interior. The moon rings like a bell. The seismic waves from a single impact can continue reverberating for an hour or more, much longer than the equivalent reverberation time on Earth. This is because the lunar interior is very dry and cold compared to Earth, with much less material that would absorb the seismic energy and dampen the oscillations quickly. The moon's interior is rigid and seismically quiet, and the waves bounce back and forth through it for an extended time before fading. Moonquakes themselves are also unusual. On Earth, earthquakes are caused primarily by the movement of tectonic plates and the release of stress that is accumulated at plate boundaries. The moon has no plate tectonics, so its moonquakes have different causes. There are shallow moonquakes caused by the thermal expansion and contraction of the outer crust as the moon moves from the extreme cold of the lunar night to the extreme heat of the lunar day. There are deep moonquakes occurring at depths of 700 to 1200 kilometers, caused by tidal forces from Earth and the Sun. And there are moonquakes caused by meteorite impacts. All of these are relatively mild by earthquake standards, but the Apollo seismometers detected thousands of moonquakes over the years they operated, building up a picture of the moon's internal structure that would not have been possible without them. The laser retroreflectors placed by Apollo 11, 14, and 15, and by the Soviet Lunokhod rovers, have been used continuously since their placement for lunar laser ranging experiments. From observatories on Earth, powerful lasers send short pulses of light toward the retroreflectors on the moon. The retroreflectors, which are arrays of corner cube prisms that return light directly back in the direction from which it came, reflect these pulses back toward Earth. By timing the round trip precisely, scientists can measure the distance to the retroreflectors with an accuracy of a few millimeters. These measurements have confirmed and refined the rate at which the moon is moving away from Earth. They have tested Einstein's theory of general relativity in the Earth-Moon system. They have measured the moon's rotation precisely enough to reveal small wobbles caused by its liquid core, and they have tracked the slow change in the moon's orbit with extraordinary precision over half a century of measurements. The Apollo program as a whole visited 6 sites on the moon. After Apollo 11 and the Sea of Tranquility, Apollo 12 landed in the Ocean of Storms. Apollo 14 landed in the Fra Mauro Highlands near a large impact crater. Apollo 15, 16, and 17 carried a lunar roving vehicle, an electric car that allowed the astronauts to drive several kilometers from their landing sites and collect samples from a much wider area. Apollo 15 landed in the Hadley Apennine region, where a sinuous rill and a mountain range provided access to a variety of geological units. Apollo 16 landed in the Descartes Highlands, the only highland landing site, providing samples of ancient crustal rocks. Apollo 17 landed in the Taurus-Littrow Valley, where the geologist Harrison Schmitt, the only professional scientist to walk on the moon, made the discovery of orange soil, tiny glass beads of volcanic origin that helped scientists understand the nature of ancient lunar volcanism. Each of the 6 landing sites provided a different window into the moon's geological history. Together, the 6 sets of samples and the 6 sets of scientific instrument deployments have given scientists a remarkably detailed picture of how the moon formed, how it evolved, and what its interior is like. This picture has taken more than 50 years to assemble and is still being refined as new analytical techniques allow scientists to extract new information from the same samples. The relationship between Earth and the moon is, in many ways, the story of a long, slow separation. When the moon formed 4.5 billion years ago, it was perhaps 15 times closer to Earth than it is today. The tidal forces it exerted on Earth were enormous, and the tidal forces Earth exerted on the moon were equally enormous. These forces have been slowly transferring energy from Earth's rotation to the moon's orbit for all of that time. Earth's rotation has been slowing, the moon's orbit has been expanding, and this process will continue far into the future. In about 600 million years, the moon will be far enough from Earth that total solar eclipses will no longer be possible. The moon will appear slightly too small in the sky to exactly cover the disk of the sun. The exquisite coincidence that currently makes total solar eclipses possible, the fact that the moon and the sun appear almost exactly the same size in our sky, is temporary, a window in geological time that we happen to inhabit. The particular stability that the moon provides to Earth's axial tilt is worth considering in detail. Earth's axial tilt, the angle at which Earth's spin axis is tilted relative to its orbit around the sun, is currently about 23.5 degrees. This tilt is what causes the seasons, and it has remained close to this value for hundreds of millions of years, varying only slightly between about 22 and 24. 5 degrees over cycles of about 41,000 years. Computer simulations of Earth's rotation without the moon show that, without the moon's stabilizing gravitational influence, the axial tilt would vary much more widely and chaotically, potentially ranging from near zero to more than 85 degrees over millions of years. An Earth with such extreme variations in axial tilt would experience extreme climate variations. Near zero tilt means almost no seasons anywhere. Very high tilt means extreme seasonal variations, with polar regions receiving more sunlight than the tropics in summer and complete darkness in winter. The complex, stable climate that has allowed complex life to evolve on Earth over hundreds of millions of years may owe something significant to the moon's quiet, steady gravitational presence in our sky. Think about what the Sea of Tranquility has witnessed over its long history. It formed as a flood of lava 3.9 billion years ago. It cooled and solidified under the ancient sky of a moon without visitors. It lay quiet for nearly 4 billion years, absorbing micrometeorite impacts and cosmic radiation and the slow weathering of space, while life evolved on Earth from simple cells to complex organisms to creatures capable of asking questions about their universe. It lay quiet while the dinosaurs rose and fell. It lay quiet while human beings evolved and spread across the earth and developed language and agriculture and writing and science and technology. It lay quiet until July 20th, 1969, when a four-legged metal spacecraft settled into its dust, and two human beings stepped out and walked on it for the first time. And then it lay quiet again. But before we reach the sleep outro, let us linger for a moment on some of the extraordinary details of this mission that are often passed over in the familiar summary of events. The Saturn V rocket that launched Apollo 11 is still, more than 50 years later, the most powerful rocket ever flown by any nation. Each of its 5 first-stage engines burned a mixture of liquid oxygen and highly refined kerosene at a rate of about 13 metric tons per second combined. In the 2.5 minutes that the first stage burned, it consumed more than 2,000 metric tons of propellant. The second stage then ignited and burned for approximately 6 minutes. The third stage ignited twice, once to reach Earth orbit and once, called the Trans-Lunar Injection Burn, to accelerate the spacecraft to the 40,000 kilometers per hour needed to escape Earth's gravity and coast to the moon. The engineering that made all of this work reliably, that ignited 5 engines simultaneously without destroying the rocket, that separated stages cleanly at hypersonic velocity, that designed the vehicle to withstand the vibration and aerodynamic forces of ascent, represented the state-of-the-art of human engineering knowledge in the 1960s. It was not done with computers the way we would do it today. The calculations were done by teams of mathematicians with pencils and paper and mechanical calculators, checked and rechecked by human beings working in offices at the Manned Spacecraft Center and at the Marshall Space Flight Center and at the facilities of the contractors who built each component. The mission was not without danger even after the landing. During the surface activity, Armstrong and Aldrin discovered that the handle of the circuit breaker that would arm the ascent engine had broken off inside the cockpit. If the ascent engine could not be armed, it could not fire, and if it could not fire, they could not leave. Buzz Aldrin solved the problem by using a felt-tipped pen to push the broken circuit breaker in. The tip of a felt-tipped pen, held between the fingers of an astronaut's gloved hand, was the last line of defense against 2 human beings being stranded on the moon. The pen worked. The circuit breaker engaged. The ascent engine fired. There is one more moment from the surface that deserves mention, a moment that is less well known than Armstrong's first words, but equally remarkable in its own way. Shortly after landing, while Armstrong and Aldrin were waiting for the surface activity to begin, Buzz Aldrin quietly unpacked a small kit he had brought with him. It contained a tiny vial of wine, a small piece of bread, and a miniature chalice. Aldrin was an elder in his Presbyterian church, and he had brought the elements for a private communion service. He radioed to Earth that he was going to perform a ceremony and asked everyone who was listening to pause and reflect for a moment on what had just happened. Then he poured the wine into the chalice, read silently a verse from the Bible, and took communion. He was the first human being to perform a religious ceremony on the moon. The wine, in the 1/6 gravity of the moon, curled slowly up the sides of the chalice as he poured it. He has described this as one of the most meaningful moments of the entire mission. The temperature variations on the lunar surface during the Apollo 11 stay were extreme. The sun was relatively low in the sky at the landing site, making this the lunar morning. Surface temperatures in direct sunlight were around 120 degrees Celsius. In shadow, they were far below freezing. The astronaut suits were designed to handle this enormous range. Using multiple layers of insulation and a system of water-cooled undergarments to keep the astronauts comfortable regardless of whether they were in sunlight or shade. The suits also had to withstand the abrasive quality of lunar dust, which is extraordinarily sharp at the microscopic level, unlike dust on Earth, which is worn smooth by wind and water over time. Lunar dust has never been subjected to these smoothing processes. Each grain is sharp-edged and irregular, capable of scratching and abrading surfaces on contact. The astronauts found that lunar dust clung to everything, including their suits, and was difficult to brush off. They brought lunar dust back into the cabin on their suits and equipment, where it produced a distinctive smell that Armstrong described as wet ashes, and Aldrin compared to spent gunpowder. The view of Earth from the lunar surface is one of the most powerful visual experiences in the account of any Apollo astronaut. The Earth hangs in the black sky, not rising or setting the way the sun does on Earth, but fixed in roughly the same position in the sky because the moon is tidally locked and always faces the same direction toward Earth. The Earth is large in the lunar sky, about 4 times the apparent diameter of the full moon as seen from Earth. It shows its cloud patterns, its blue oceans, its brown and green continents. It rotates visibly over the course of a day if you watch it long enough, its cloud patterns changing as new weather systems rotate into view. It is the most familiar and the most alien sight imaginable simultaneously. Familiar because it is home. Everything you have ever known, the blue world that contains all of human history. Alien because you are looking at it from 384,000 kilometers away from the surface of another world, with a black sky around it that contains no blue, no haze, no scattered light. Every Apollo astronaut who has described the experience of seeing Earth from the moon has used similar language. Small, fragile, precious, isolated, the sense that this blue sphere is all there is, hanging in an immense darkness, containing every human being who has ever lived, except for the small number standing on the moon looking at it. The experience changed every one of them in ways they found difficult to fully articulate, but impossible to deny. The overview effect, as it is now called, the cognitive shift that comes from seeing the Earth as a whole object from outside it, as a single fragile world rather than an infinite stage, is one of the most consistent reports from astronauts across all national backgrounds and all missions. Neil Armstrong himself was notably private about the personal meaning of the mission. He did not seek fame. He gave very few interviews after returning from the moon. He declined most opportunities to speak publicly about his experience. But in the rare moments when he did speak about it, he described the mission not primarily in terms of personal achievement, but in terms of the human collective achievement it represented. He was always careful to say "we" when talking about the mission, referring to the 400,000 people who had worked on the Apollo program rather than I or the three of us. He understood that he was standing at the apex of an enormous pyramid of human effort and knowledge and sacrifice, and he did not want the pyramid to be forgotten in favor of the three people at its apex. When Armstrong died in 2012, at the age of 82, his family released a statement that has been widely remembered. It described him as a reluctant American hero who always believed he was just doing his job. And it ended with this request: the next time you walk outside on a clear night and see the moon smiling down at you, think of Neil Armstrong and give him a wink. You are very close to sleep now. Let everything be still. Let the moon drift gently into the peaceful space behind your closed eyes. The Sea of Tranquility, dark and quiet and ancient, the footprints still there after half a century. The Earth rising above the lunar horizon, a blue and white sphere suspended against the absolute black of space. Silence so complete that you could hear your own breathing in your suit. The sun blazing with an intensity unfiltered by any atmosphere, casting hard, sharp shadows from every rock and crater rim. This is the moon that hangs in the sky above you tonight. The same moon, the same Sea of Tranquility, the same ancient volcanic plain where two human beings once stood and looked back at the world they came from. It is there right now, quietly orbiting, pulling the tides, keeping the seasons steady, drifting slowly outward at 3.8 centimeters per year, doing all the things it has been doing for 4.5 billion years. And somewhere on its surface, in the southwestern part of the Sea of Tranquility, there are footprints, preserved in the fine gray dust for longer than anything built by human hands will last. A message from the first chapter of our journey outward. We were here. We came this far. We will come further still. Sleep now. Let the moon keep its watch. Let the Sea of Tranquility be exactly what its name says. Let everything be still. Good night.